Hello and welcome to lesson number 6, the sine rule and the cosine rule. These two are two geometric facts that are true about triangles which we can use to derive relationships between the side lengths and angles of triangles. So let's begin. First we're going to be talking about the sine rule. The sine rule and cosine rule of course have to deal with triangles, so let's talk about the sine rule first. Consider a triangle like this. This triangle, it can be any shape. So let's just construct one at random. There we go. This triangle I'm going to label with the names of points A, B and C. And I'm going to suppose that the angle here is going to have the same name as its point. So it's going to be capital A. The angle here is going to have the same name as its point. So it's going to be capital B. And the angle here is going to have the same name as its point, so it's going to be capital C. And I'm going to suppose that the length opposite to an angle be referred to by the simple letter of its same symbol. So the opposite side to angle A will be referred to as simple A. The opposite side to angle B will be referred to as simple B. And the opposite side to angle C will be referred to as simple C. The sine rule states, given this, that sine A divided by A is in fact equal to sine B divided by B is in fact equal to sine C divided by C. Here note, this capital A is referring to the angle capital A at the point capital A, and the simple A here is referring to the side length opposite to that angle. Similarly, this capital B is the angle capital B, and this side length simple B is the side length opposite to the angle B, and C is the angle C, and simple C is the side length opposite to the angle C. So now let's look at how we can prove that this fact is true. So to prove this fact is true, I have constructed a triangle here, the triangle A, B and C, and I'm going to label the side lengths also. This is C, this is A and this is B. I've taken the base BC to be horizontal just for the ease of construction. The first construction I'm going to do, which you can do with a compass and a ruler too, is to construct the perpendicular from A to the line BC. So this line is perpendicular to the line BC. So here we have 90 degrees. Now all I'm going to do is just construct just draw the angles in. This is what I called capital B. The other angle is what I call capital C. And I'm going to suppose that this point here, where the perpendicular of A intersects the line BC, is going to be the point D. I'm going to suppose that's point D. And I'm then going to suppose that I call the height AD as H. All good? All good so far. So now I'm going to consider what sine of B and sine of C are in this situation. So in this situation, sine of B, well, the sine of an angle within this triangle is simply the opposite side divided by the hypotenuse. Since this is 90 degrees, it is a right angle triangle. So therefore, the sine of B here is H divided by side length C. Similarly, considering in another way, if I take the sine of C, what is sine of C? The sine of the angle C on the other side is the opposite divided by the hypotenuse. So the sine of C is opposite, which is H, divided by the hypotenuse, which is B. So we have these two relations. Both of these are true, of course, which means we can write H in two different ways. From this first equation, we get that H equals to C times sine capital B. From the second equation, we get that H is equal to B sine of capital C. From these two, we can see on the left side both are H, on the right side we have C sine B and B sine C. Therefore, it should be the case that C sine B is equal to B sine C. Rearranging, we can clearly see that sine B divided by B is equal to sine C divided by C. In a similar way, if we construct the other two perpendiculars, we can find the exact same thing to be true. Constructing this perpendicular, which will be something like this. Actually, I think this, in this case, it will be outside of the triangle. And constructing this perpendicular, it will be something, actually this one also looks like it's outside of the triangle, but no matter, it will still produce us the required result. Using this, without loss of generality, we can find, this is 90 degrees here, and this is also 90 degrees. Using this method, we can find that this value here, b divided by sine b divided by b and sine c divided by c, are also equal to sine a divided by a. I will not be going over that one, but it's done in the exact same way that we found that sine b divided by b is equal to sine c divided by c. So by constructing the other two, we can see that this is also true, and therefore sine a divided by a is equal to sine b divided by b is equal to sine c divided by c. And here we did not make any limitations other than this shape being a triangle, so therefore this is true for all triangles. There is of course the one case where we have one of the sides being length 0, in which case one of the angles will also be length 0. In that case, that value will be 0 divided by 0. It will be sine of 0 degrees divided by 0 degrees, which is 0 divided by 0. But putting that aside for now, if you look at only the other two, that fact will of course still be correct. So yes, we do have that issue where if one of the side lengths is 0, we have a problem. Other than that, we do not have a problem, and this will work for any triangle. Now that we have proven the sine rule, that sine a divided by a is equal to sine b divided by b is equal to sine c divided by c, where capital A, capital B, capital C are the angles at the points capital B, capital A, capital B, capital C, and the simple A, simple B, simple C side lengths are the lengths of the sides that are opposite to the angles capital A, capital B and capital C respectively. So now we'll move on to the second rule that I mentioned, the cosine rule. It is again due to triangles. I'll state the cosine rule first and then we'll prove it. The cosine rule states, again, given a similar triangle setup, let's call this point A, let's call this point B, and let's call this point C. And that means that this angle is A, this side length is simple A, this angle is B, this side length is simple B, and this angle is C, and this side length is simple C. Given this configuration, it is the case that C squared is equal to A squared plus B squared minus 2AB cosine of the angle C. Similarly, the other two are also true. A squared is equal to B squared plus C squared minus 2BC cosine of angle A, and B squared is equal to A squared plus C squared minus 2AC cosine of B. You can see why this one gets its name as the cosine rule, because it has a cosine in it. That's literally it. So this geometric fact is true, and you can see a little nicety here that when this angle is 90 degrees, we get the case that this is a right angle triangle, in which case cosine of 90 degrees will become 0, in which case these terms cut, and we get that C squared is A squared plus B squared, hence Pythagoras' theorem. So this shows us Pythagoras' theorem is also true within itself. Of course, we use Pythagoras' theorem to derive it, but it confirms Pythagoras' theorem. You shouldn't have some theorem used to derive something else, and then that second theorem disproving the first one. The second theorem should contain the first theorem or should agree with the first theorem. We shouldn't have a contradiction. And we do not. We can clearly see when this angle cosine C is 90 degrees, cosine of C is 0, which then means that C squared is A squared plus B squared, hence Pythagoras. So now let's prove the cosine rule. So to prove the cosine rule, we're actually going to do the exact same construction we did earlier. Let's consider a triangle ABC. So I'm going to draw a triangle ABC. We're going to, for convenience, make this side length horizontal. Let's say we label these points in that normal format, calling this point here A, this point here B, and this point here C. So then this side length would be C, this side length would be A, and this side length would be B. And we're going to construct the perpendicular from A to the side length BC. So then we have constructed a perpendicular, which means that this angle is 90 degrees, this angle is 90 degrees. But now we're going to do something else. We're of course going to label this point D as we did earlier, but now we're going to label a different length. We're going to label the length DC. We're going to label it as some x. We're going to label it as x. So the total length BC was A, which means if we take away that part DC from BC, what we are left with is the difference of A and x. So this is A minus x. Since the total length BC is A, we've taken away x, which means the remaining is A minus x. So now let's use our trigonometric relationships to try to find what each of these values are. So here this angle is C, this angle is B, and we are going to ignore angle A for now. Considering the triangle ADC, within triangle ADC, if we try to figure out what cosine of C is, let's just write that down. Cosine of C is adjacent divided by hypotenuse. Adjacent is x, hypotenuse is b, so therefore cosine of C is x divided by b. Now from this we can get that x is equal to b times the cosine of C. Let's call this 1 and leave it for now. Next, let's consider the other triangle ABD. So in triangle ABD, we can see that AD is a height, BD is a base, and C, the side AB, is our hypotenuse of this right angle triangle. So now we're going to try to find the side lengths of this. We already know A minus x because we know x and A is a known value. What about the height AD? Well, if we just temporarily label that H and consider this triangle here, we have that H divided by B is the sine of C. So then we have the sine of C is the opposite, which is H divided by the hypotenuse, which is B. So H divided by B, which then gives us that the side H is B sine C. We'll call that 2. Now we know the side lengths AB, BD and AD, and we know that this angle here ABD is a right angle triangle. So ABD triangle is a right angle triangle. From this we can apply Pythagoras' theorem and say that AB squared, the hypotenuse squared, is equal to the other side length squared summed. The other side lengths are BD and AD. So we have BD squared plus AD squared. Now let's substitute what each of these side lengths are. AB is C, so we have C squared is equal to BD squared. BD squared is A minus x. BD is A minus x, and x is B cos C. So we're going to substitute that directly. Instead of x, A minus B cosine of C squared plus AD. AD is H and H is B sine C. So we're going to directly substitute. We're going to do two substitutions in one. AD is H and H is B sine C squared. So now we have C squared is A minus B cos C squared plus B sine C squared. If we expand both sides here, what we get is that C squared is equal to, and A minus B cos C squared will be A squared minus 2AB cosine C plus, and then minus B cos C squared, which will be B squared cosine squared C plus, and B sine C squared will be B squared sine squared C. So we have this relationship. Notice here we have B squared cos squared C and B squared sine squared C. I'm going to pair them up. I'm going to take out the common factor B squared and bring it here. So when we do that, we get that C squared is equal to A squared plus B squared times sine squared C plus cosine squared C plus, actually minus 2AB cosine C. So remember and recall the identity that we talked about earlier, that sine squared plus cosine squared for any angle theta will be 1. Recall, sine squared theta plus cosine squared theta is equal to 1, and substitute into here. Substituting it into here, this whole thing sine squared c plus cosine squared c would be equal to 1, meaning we have b squared times 1. B squared times 1 is simply b squared. Therefore, we finally get that c squared is equal to a squared plus b squared minus 2ab cosine of the angle c. We have proven the cosine rule. And of course, once again, by the same construction, if you draw the other two right angles over here, if you draw this one which will look something like this one which will actually look something like that, you can find the other two in the same way. So in the same way that we proved that c squared is a squared plus b squared minus 2ab cos c, it can also be shown that b squared is a squared plus c squared minus 2ac cosine of b, and also that a squared is b squared plus c squared minus 2bc cosine of a. It can be shown. So now we have proven the cosine rule as well as the sine rule, and I hope you take away from this these two identities, and I hope you use them in your required activities. And that will conclude our lesson for today. We have learned the sine rule and cosine rule, two basic and simple rules of trigonometry in any triangle where one of the angles and sides is not 0. That's kind of important. We have that the sine of the angle A divided by the side length of the side opposite, which we label simple A, is equal to the sine of an angle B divided by that side's opposite side length, that angle's opposite side length. And it's true for all three. Sine A divided by A is equal to sine B divided by B is equal to sine C divided by C. Note the convention where the capital letter is used for the angle and the point, and the simple letter is used for the side length opposite that angle. Similarly, given that same convention, we can see that c squared is a squared plus b squared minus 2ab cos c, and the other two pairs of the same equation for any given triangle. Of course, in this case, however, it will not cause an issue when one of the side lengths is equal to 0. This is because if one of the side lengths is equal to 0, we just have, let's say b is 0 in this case. If b is 0, this thing becomes 0. And similarly, this thing containing b becomes 0, so this is also 0. Which means that c squared is a squared, which is of course true, because if we have a triangle where one of the side lengths is 0, the other two lengths are equal to each other. So we have a truth. So we can derive that. It's no problem here. However, one of the sides being length 0 is an issue when we have the sine rule. So avoid that. Other than that, there's no other things to note. So that's the end of this lesson. Thank you for watching and goodbye.